This lesson relates to problems with the presentation of descriptive statistics that can occur in reports of statistical data. After completing this lesson, you will be able to identify the following problems when reading statistical reports. First, you will know how the use of the wrong average could influence your results. Second, you will know how to identify manipulations in graphs and graphics. Before we discuss descriptives, let's quickly review what they are. When examining statistical reports, we often encounter two types of statistical data, descriptive and inferential statistics. Descriptive statistics help us quickly make sense of data by summarizing patterns among the numbers, whereas inferential statistics takes the analysis a step further and helps us understand how different variables are related. This lecture will focus on descriptive statistics. There are three main ways to describe data. These are the average, this is the most representative score in the data set, variability, which is how data is spread out from the average, and shape, which is how does the data look when it's graphed. We'll discuss these in more depth later, but for now we'll focus on problems that can arise when you use the wrong average or when the graph or graphic used to represent the data is manipulated. Let's begin with averages. As you may recall from Stat 200, there are three main types of averages: the mean or arithmetic average, the median or the middle score, and the mode or the most frequently occurring score. These averages may represent largely different numbers in a distribution, and the use of the wrong average could lead to inaccurate conclusions. For example, ever heard of the statistician drowning in a pond with an average depth of 3 feet? Or the statistician that put his head in the fridge and feet in the oven and said, "On average, I feel pretty good." In these situations, the average that is being used is the mean. However, the mean is strongly impacted by extreme scores in a data set and is therefore not a representative estimate of the entire set of data. An example of this problem has also been seen in the news. In July 2013, Detroit's emergency manager Kevin Orr said that part of the reason the city needed to declare bankruptcy is that the local police department was badly lagging behind national norms for response times. According to Orr's report, Detroit police took an average 58 minutes to respond to calls compared to a national average of 11 minutes. While there were a host of problems with this statistical report, including problems with the definition and measurement of response time, one of the larger problems here is the type of average reported. In this case, the report presented the average using the mean, but the mean is easily inflated by even just one data point that is much larger than the others in the distribution. In such situations, the median provides a much more accurate representation of the average than the mean. Let's put this in context with a sample data set. Let's say a random sample of 4 recent SRA grads were given a salary survey asking them to report their starting salaries. The results from the survey are presented here in Scenario 1. Using this data, we can compute the average starting salaries for SRA students. The mean would be the sum of all the scores divided by the total number of scores, which would be $66,000. The median would be the number in the middle of the distribution after the scores have been sorted from highest to lowest. In this case, we have an even number of scores, so we would compute the median by finding the 2 scores in the middle of the distribution and divide them by 2. which also gives us $66,000. Finally, the mode is the most frequently occurring number in the distribution, which also turns out to be $66,000. It is not uncommon that in normally shaped distributions that the mean is equal to the median, which is equal to the mode, or that the values are close together. Now let's say two more students decided to complete the salary survey. The results from the full survey that include these additional students are shown in Scenario 2. Once again, we can compute the average starting salaries for SRA students from this data. The mean for the new set of salaries is $101,500. The median is $70,500. And the mode is $66,000. Let's compare both sets of averages from Scenario 1 and Scenario 2. Here you can see that the addition of students 5 and 6 had a large impact on the mean, only a little impact on the median, and virtually no impact on the mode. Let's consider a third scenario. Now, let's say the two students that decided to complete the salary survey in Scenario 2 were replaced by two other students that got even higher starting salaries. The results from this survey are shown in Scenario 3. After computing the average starting salaries from this data, we can see that the median and mode have remained unchanged between Scenario 2 and 3, but that the mean has increased by $40,000. That's a big amount. So what can we conclude from this? Well, with any distribution of scores that contain outliers, which were the extreme values that were added to Scenario 1, the mean will be pulled in the direction of the extreme scores. The more extreme the scores, the greater the pull. The median will be only slightly pulled in the direction of the extreme scores. As shown in Scenario 3, unlike the mean, the value of the median is not impacted by the size of the extreme values, and the mode is not impacted by extreme scores at all. When deciding what average to choose, the mean is often the preferred estimate because it takes into account every score in a data set in its calculation. It is therefore oftentimes the most representative value of the average. However, when extreme scores are present, the mean can misrepresent the data when used as the average. In such situations, it is best to use the median. Later in the course, we will discuss when we will use the mode and other uses for the median value. Now you have an understanding of how the wrong average can produce misleading results. Let's discuss how graphs and graphics can be manipulated. Now we'll discuss 4 of the most common problems that can occur with the display of graphs or graphics. The first is an exaggerated image size. This is discussed in Chapter C3 of the Joel Best textbook. Oftentimes, statistical results can be difficult to understand without some visualization of the data. Eye-catching displays are often used to condense streams of numbers. These are often used instead of the more traditional visual displays of graphs and tables. However, these displays are often not to scale and therefore exaggerate the importance of a particular group of data. Here's an example from your text. This is a graphic summarizing the results of a study on crystal meth use among gay men in New York City. The results of the study showed that among the individuals that admitted to using crystal meth, twice as many were HIV positive as opposed to being HIV negative. The problem with this graphic is that the crystal meth rock used to represent HIV positive men is not only twice as high as the other rock, but it is also twice as wide. This graphic is therefore suggesting that the HIV positive men in the survey are 4 times as likely to use crystal meth than HIV negative men. A similar issue can be seen in another example. In discussing the state of women in the nation, NBC reported that 4 out of 10 mothers are now the primary breadwinners in their families. It is an alarming statistic. However, as you can see here, the presentation of these results includes an exaggeration of the size of these 4 women, which also visually inflates the results. Maps are another creative way to visually present data. However, one of the biggest problems with maps is that often the largest states have the smallest populations. As illustrated here, the same population is highlighted in both maps of the United States. The population of the highlighted states in the first map is the same as the population of the highlighted states in the second map. This map is a bit dated, but it aptly shows the dangers of associating land mass with population. Here is an updated version of a map of the United States. This photo is taken at night. It also helps to show that larger states often have the smallest populations. The inappropriate use of maps is often quite prevalent in statistical reports. In discussing the obesity problem across the nation, NBC used the following map to highlight where the most obese people live. The colors represent different gradations of the severity of the problem, with red and orange representing where the highest percent of obese people live, and green and blue representing where the lowest percent live. As previously discussed, through the use of a map, this visualization overrepresents the number of people that are obese by ignoring the fact that the largest states often have the lowest populations. It would therefore take fewer obese people in larger states, such as Texas, than in smaller, more densely populated states, such as New York, to fall into the orange or red categories. A third common problem with visualizing data is the use of inappropriate intervals on the y-axis. Large intervals on the y-axis understate the differences between the numbers, whereas small intervals over-exaggerate these differences. Be wary of statistical reports that manipulate the size of these intervals to support their claims. Here's an example of this taken from 2 different 1930s reports on government payrolls. Both graphs are based on the same set of data, but tell different stories solely by manipulating the size of the intervals on the y-axis. A similar problem is shown with these graphs. In the first graph, the number of homicides across the years seems to be drastically increasing, whereas in the second graph, the number of homicides across the years has remained stable. Later in the course, you will learn to not rely as heavily on visual interpretations of data, but rather determine whether or not there is a true upward trend in the data through the use of significance testing and probability theories. Other problems that can occur on the y-axis include the use of a disproportionate scale. This can be fairly subtle to detect. For example, this graph suggests that the unemployment level has remained more or less stable across time and has not changed much since its dip in March. However, closer examination of the chart shows that the values shown in November should actually be listed below those shown in March. Here the reporters are using a disproportionate or inaccurate scale. Can you detect the problem with the y-axis in this graph? This was produced by the AIM group to show the relationship between Craigslist revenue and newspaper ad sales. The argument being made is that newspaper ad sales have fallen below Craigslist revenue. However, two different scales of measurement are being used in this graph. Craigslist revenue are listed in millions, and newspaper ad sales are in billions. Therefore, there should actually be no overlap between the two lines on this graph. The fourth most common problem that can occur with graphs is the manipulation of the x-axis. This is often done by selectively reporting data and excluding others. This graph shows that there is a linear trend in the number of hurricanes that have occurred between 1992 to 2000. On closer examination of the x-axis, you can see that the years aren't listed in logical intervals. For example, there is a gap of 2 years between 1992 and 1994, but a gap of 1 year between 1994 and 1995. Here is the same graph with all the data from the missing years added. You can now see that instead of a linear trend in the number of hurricanes that have occurred across the years, there is now no discernible pattern. These are only a few of the many ways graphs can be manipulated, but by keeping these pointers in mind, you can be a better consumer of statistical reports.